Hi, this is Surya. Welcome to my channel Sigma Modulo. In this video, we are going to discuss one of the millennium problem, that is unsolved problem in the list of unsolved problem in Clay Mathematical Institute. That is a Reiman hypothesis proposed by Bernhard Reiman, proposed by Bernhard Reiman, Bernhard Reiman, and he's a German mathematician who made contribution to analysis, number theory, differential geometry. And Riemann had published a paper in 1859 on the prime counting function, and it contains the original statement of this Riemann hypothesis. This Riemann hypothesis, which is regarded as one of the most influential papers in analytical number theory, and he mentioned this zeta function there on his paper. And Bernhard Reiman was one of the greatest mathematician of all time, and he investigated the zeta function, that is zeta function. He investigated the zeta function that now bear his name, and establishing its importance for understanding and the distribution of prime numbers. Distribution of prime numbers. And the Riemann hypothesis was one of a series of conjectures he made about the function properties. What the hypothesis says, all non-trivial zeros of the zeta function, this one, have real part 1/2. This means for which value of s the zeta function becomes 0. This is the hypothesis, and we'll discuss about it. Before discussing the hypothesis, let's begin with the prime number. Let's begin with the prime number. What is prime number? Okay, before that, take a whole number, positive whole number. Take a positive whole number. Let's say 28. Let's say number, positive whole number. Positive whole number. Whole number. Let's say 28. And now the question is, what numbers divide exactly into it? What numbers divide exactly into it? It gives 1 into 28 is 28, 2 into 14 is 28, 4 into 7 is 28. As we see, 28 has a factor, and factors are 1, 2, 4, 7, 14 and 18. These are the factor. So we can say that 28 has a 6 factor. 28 has 6 factor. And every number has 1 as a factor, and every number has itself as a factor. Okay, let's say 29 as number. 1 into 29. You see, every number has 1 as a factor, and every number has itself as a factor. Number itself as a factor. Okay, and these are called, in mathematics, these are called trivial factor. Trivial factor. These are called trivial factor. What about 2, 4, 7 and 14? Here 2, 4, 7 and 14 as proper factor. Proper factor. Okay? Proper factor. And on this number, nothing divides 29 except 1 and the number itself. Therefore, we can consider this as, it's not we can consider, it is itself a prime number. Prime number. Prime number. Now we know what is prime number. Prime number is one with no proper factor. It's a no proper factor. No proper factor. Prime number has trivial factor. That is the number itself and 1. Okay, let's do an exercise here. If we calculate the number of primes from 0 to 100, let's say from 0 to 10, calculating the prime number from 0 to 10, how many number will get? From 0 to 10, number of prime, how many prime numbers are there in between, from in between 0 and 10? 2, 3, 5 and 7, 4. Okay, 4. And what about from 0 to 100? From 0 to 100, it's 25 primes. Number of prime is 25. Number prime 25. What about 0 to 1000? From 0 to 1000, number of primes are 168. As we closely look at the list of the primes, one can see that they thin out as one go along. Suppose from 0 to 10, 4, 0 to 100, 25, from 401 to 500, number of primes 17, from let's say 901 to 1000, number of primes will be 14. Okay, 4, 25, 7, 14. Okay, now the question arises here, do the prime eventually thin out to nothing? This is the question. Let's say if I count the list into the trillions of trillions of trillions of trillions, would I eventually reach a point beyond which there are no primes? This is the question. If I count the trillions of trillions of trillions of trillions, would I eventually reach a point beyond which there are no primes? As an answer to this question, Euclid around 300 before common era, 300 before common era, Euclid had said that the primes never thin out to nothing. He said that the primes never thin out to nothing. Thin out to nothing. This is Euclid's proposition. and there are always more. There are always more. The prime go on forever. Prime go on forever. Go on forever. Primes go on forever. And having had that point settled so early in the history of mathematics, the next thing mathematicians were eventually curious about was can we find a rule, a law to describe the thinning out? That was about the mathematician who were curious about. And is there a rule or a formula to tell how many primes are there less than a given number? And this this is where Bernhard Reiman started. This is where Bernhard Reiman started. What was the question? The question was, is there any formula to tell, or is there any rule to tell that how many primes are there less than a given number? And Bernhard Reiman started with this one: how many primes are there less than a given magnitude? How many primes are there less than a given magnitude? Given magnitude. Here we should remember one of the greatest mathematician of all time, and he's Carl Frederick Gauss. One of the greatest mathematician of all time, Carl Frederick Gauss, and he counted the primes up to 3 million. Counted the primes up to 3 million. And by the middle of 8th century, 18th century, quite a lot of mathematicians were thinking about infinite series, and series looks like, and the series kind of looks like Carl Frederick Gauss. Here Carl Frederick Gauss is regarded as a prince of mathematics in his time, one of the greatest mathematician of all time. And next thing, the mathematician were trying to think about the infinite series. This is an era where mathematicians were thinking about infinite series. Century, and the series is kind of like 1 plus 1 divided by 2 to the power n plus 1 divided by 3 to the power n plus 1 divided by 4 to the power n, and it goes on and on. This is an infinite series. In the series, if we put n is equal to 2, we get the Bessel problem here. Bessel problem. By putting n is equal to 2, that is 1 plus 1 divided by 2 to the power 2 plus 1 divided by 3 to the power 2 plus 1 divided by 4 to the power 2 plus, and goes on. The sum of the reciprocal of the square of positive integer, that is Bessel problem, and this one is solved by Leonhard Euler. In 1734. We have already discussed the Bessel problem in 3 parts in our previous videos. One, if anyone is interested, they can check out my channel, and they'll get the 4 solutions that given by Leonhard Euler in my channel. Here, when putting n is equal to 2, the series becomes like the sum of the reciprocal of the square of positive integer, and Leonhard Euler has given the value here 1 plus 1 by 2 to the power 2 plus 1 divided by 3 to the power 2 plus 1 divided by 4 to the power 2 goes on is equal. We can write a summation of n is equal to 1 to infinity divided by n square, which gives a value of pi square by 6. Pi square by 6. He has given the value. And if we put on the series, this is a series, if we put n is equal to 1, what will get? 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus up to infinity. And this becomes a harmonic series. This becomes a harmonic series, and it diverges, and it is divergent series. It's a divergent one. Therefore, this can't have a finite value. This series can't have a finite value. Cannot have a finite value. Because of divergency. And if we put the value n is equal to 3, what do we get? If we put the value n is equal to 3, 1 plus 1 by 2 to the power 3 plus 1 divided by 3 to the power 3 plus 1 divided by 4 to the power 3 plus, it goes on. And this series gives a value of 1.202056, and it goes on. Okay, and putting n is equal to 4 on this series, 1 plus 2 to the power 4 plus 1 divided by 3 to the power 4 plus 1 divided by 4 to the power 4, and it goes on. And this gives a value of 1.08232232, and it goes on. This goes on. And if we put the value on a real number line, this is 0, this is 1, 2, the value of this series will lie in between 1 and 2 on the number line. Okay, and let's now talk about Reiman hypothesis. Reiman hypothesis, what it says here. Reiman hypothesis. Reiman hypothesis. Reiman introduced the zeta function for s is greater than 1, for s is greater than 1, zeta of s is equal 1 divided by 1 to the power s plus 1 divided by 2 to the power s plus 1 divided by 3 to the power s plus 1 divided by 4 to the power s, and it's infinite. And the hypothesis says that all non-trivial zero of this zeta function, have a real part 1/2. Okay, real part 1/2. Let's put it in a simple way. This is a summation of n to the power minus s. Okay, applying a process very much like the siege of Eratosthenes to this sum, then it will equivalent to zeta of s is equal to 1 divided by 1 minus 2 to the power s into 1 divided by 1 minus 1 divided by 3 to the power s into 1 divided by 1 minus 1 divided by 5 to the power s into okay, and that is zeta of s is equal the product of p goes from 1 to infinity 1 minus p to the power minus s inverse. Okay, when the term of the infinite product run through all the primes, and so we can deduce integration of summation of n goes from 1 to infinity n to the power minus s is equal product of 1 minus p to the power minus s inverse, that is p prime. Okay, this is prime, and the hypothesis states that states that all non-trivial zeros of the zeta function have real part 1/2. This is the zeta function. This is the Reiman hypothesis states. Let's turn our attention to the argument of s on the function. When s is equal to 1, the zeta function becomes 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus and up to infinity, and this series is diverges. as we have already discussed, this series is diverges, and therefore zeta of 1 zeta of 1 1 zeta of 1 has no value, okay. If we put the value here, if we put the value of s, if we put s equal to 2, 3, 4, and from 2, 3, 4 it always converges, and we can have value for that series from s equal to 2 to 2, 3, 4 to infinity has value at some point because of convergence. Convergent. Okay. Now, what happens if we put s equal to 0? If we put s equal to 0, the function becomes, the series becomes 1 plus 1 plus 1 plus 1 plus 1 infinity. This also pretty obviously this series is diverges. So this can't have any value. Now we can see that every negative number, if we put the value of negative number on the zeta function, that is minus 2 gives a value of 0, minus 4 gives a value of 0, and minus 6 gives a value of 0, and so on. And when when we substitute the value of s, that is minus 2, minus 4, minus 6, negative even integers, we get the value of this function 0, and these zeros are called the trivial 0. If we put in line here, this is 1, this is 2, minus 1, minus 2, up to here, this kind of value. This says from here the function has some conversion value up to this shaded portion, and here on this shaded portion it gives a trivial 0. Gives a trivial 0. Now from the hypothesis, the question arises here, where are the non-trivial zeros? Because the hypothesis says all non-trivial 0, and the hypothesis says the all non-trivial 0 of the zeta function have a real part 1/2. Hypothesis says about non-trivial 0, and we get trivial 0 when we put the value of s is negative even integers. Negative even integer. Gives a trivial zeros. And now our search is to find the non-trivial 0. For that, to understand the non-trivial 0 on the function, let's take a complex plan. That is this is a real this is the imaginary axis. Suppose this one I, this is twice I, it goes like this. Here 1, 2, 3, this is here -1, -2, -3. The zeta function here is s is equal to 1 divided by 1 to the power s plus 1 divided by 2 to the power s plus 1 divided by 3 to the power s plus 1 divided by 4 to the power s up to infinity. And for this complex plane, let s is equal to here, let s is equal to a plus ib is a complex number, where a comma b is a real number and I is equal to under root minus 1. And from this function we can have the value, putting the various value on this series, that is s equal to 1, s equal to 2, s equal to 3. We have already discussed. If we put the value of -1 here, if we put a value of -1, s is equal to -1, it gives a 1 plus 2 plus 3 plus 4 plus to infinity. This is a divergent series, and Ramanujan had given a value for this series which is equal to -1 by 12. Ramanujan summation, and we have already discussed the summation of Ramanujan, but in general this series is divergent. This can't have a value, no value on it, since it's a divergent, and the value is undefined. Here. And putting the value of 2 we already discussed, that becomes a Bessel problem, and we have already discussed the Bessel problem. And let's turn our attention to this complex plane. Reiman said on his paper that we should allow not only natural number to this function, not only natural number for s, but real number and the complex number also we should allow. And then what he say, he says that what values of s gives 0 for non-trivial 0 when the real part becomes half. It says half. Suppose this point is half. If we put a line here, this 1, and here real part s is greater than 1, and this on this portion the series have a convergent value. The series has a convergent value on this portion, and this part will give any convergent value when real s is greater than 1. And this portion we have already discussed. the value here. Minus 2 is 0, minus 4 is equal to 0, minus is equal to 0, and this portion gives it trivial 0, trivial 0, trivial 0. This portion gives it trivial 0. This is sometimes called the obvious 0, sometimes called the obvious 0. And hypothesis says that all non-trivial 0 of the zeta function have a real part 1 by half. If we draw a line here that is regarded as a critical line, this is regarded as a critical line, and the hypothesis states that at this line, in this critical strip, there could be infinitely many zeros. This is the mystery also at this point. And the Reiman hypothesis concerned with the location of non-trivial 0. It's concerned about location of non-trivial 0. Non-trivial 0. Concern. Reiman hypothesis concern about the location of non-trivial 0. And the hypothesis makes a stronger assertion that they all lie on this line, whose real part is 1/2. So real part is 1/2. And on this critical line, all non-trivial 0 lies at this point. This is this on this line, all non-trivial 0 lies. And if we see the diagram for the point that come from that critical line, this is 1, this is 2, minus 1, minus 2, I, twice I, and here real part r of s is greater than 1. It has a conversion value on this portion, and it has obvious 0, gives a value of obvious 0, which is trivial 0. And the hypothesis is at real part half at this point. If we draw a line here, the hypothesis is all point lie on this critical line, all zeros, all non-trivial zeros, non-trivial zeros lie on this plane. And this shows and if we draw the points, that is a that comes from this critical line, it kind of look like this. It kind of look like this. It kind of look like this. That is points come from the critical line, critical line. The hypothesis says that the real part for every non-trivial 0. The hypothesis says the real part for every non-trivial 0 is 1 by 2, and the zeta function, zeta of s, will be half. Okay, if the hypothesis is correct, all the non-trivial zeros lie on this critical on this critical line. This is a critical strip on this critical strip, and this critical line consisting a complex number. Suppose the complex number will be like half plus minus it. You can say, one can say half plus minus alpha plus minus t. T is a real number, t is real, I is imaginary, and therefore the zeta of s is defined for complex x. Zeta of s is defined for complex s, and whose real part is greater than 1. That means zeta of s is equal 1 divided by 1 to the s plus 1 divided by 2 to the s plus 1 divided by 3 to the s plus 1 divided by 4 to the s plus infinity. And Reiman said that at the critical line, at the critical strip, there could be infinitely many zeros on that line, and he has a clear cleared that on the critical line there could be many infinitely zeros, non-trivial zeros. And this is the hypothesis, and this is the millennium problem. And at what point on this line, the zeta of s will be 0 with real part half. And this is the hypothesis, and this is the millennium problem. This is 1 million prize problem. Thank you so much. Thanks for watching. Please like, share and comment. If you did not subscribe my channel, please subscribe it. Thank you so much. Have a great day.